Welcome back to Deep Learning for Computer Vision. All right, now it's getting a little bit advanced. It's getting pretty interesting and the likes. In the last video, we talked about convolutional neural network, which is one of the fundamental parts with respect to modeling an image, right? We spoke about how images can be learned, how models can be written, via computer vision. All right, this time around, we are going to be doing it a little bit much more interesting, and we're going to be talking about transfer learning with pre-trained models in computer vision. Most times, as a computer vision person, you might most likely not build foundational model, right? Sometimes you might want to actually leverage on the usage of pre-trained models, right, in order to be able to build a much more robust or a much more tailored computer vision model. And that is all we're going to be learning in this particular course. Stay tuned and sit back as I analyze everything for you.
Welcome back to class. All right, in today's class, we would be looking at deep learning for computer vision, and the aspect we are going to be looking into primarily is transfer learning with pre-trained models. That's what this video is all about. So, what are we going to be learning in today's class? We're going to be working with a data set called cat versus dog, cat and dog data set, and we're going to be trying out the classification. We're trying to build a CNN model, build a model that can distinctly identify a cat from a dog. We're going to be using CNN, so we're going to be training a CNN model. Next is that we're going to be trying out we're going to be training this CNN model. The first one is training the CNN model from CNN, like scratch CNN. The next one is that it's going to be a CNN model, but it's going to be a transfer learning model. And I'll be talking a little bit about what transfer learning model entails or looks like. So, for you to build a classification model using CNN, first and foremost, you need to be able to load the data sets. So you need access to a data, and in this case, we are going to be working with the cat and dog data set. All right. Next is the data pipeline. The data pipeline is basically what happens to a data from its raw form up to the point of the testing form of the data. If trying to predict, run inference from its raw form up to the point of inference, which is predicting if it is a cat or a dog that is in the image. So data pipeline, basically you're trying to create a data pipeline of this is the input data, and then the next thing is you are preparing the data. So maybe you are trying to resize, grayscale, or some of those things. That's data preparation, and then you feed that into the model. That is, you have to create the model architecture. That is the CNN model or transfer learning model. You have to script that out, feed in the image or the data into the model, and then the output of the result, which is a binary classification, whether it's a 0 or a 1. So this is a binary classification problem. We're trying to say, okay, if it is a cat, it's a 0. If it is a dog, it is a 1. All right. So binary classification. So that's the data pipeline up to the point of running inference on any image that is a cat or a dog, and you're trying to evaluate if this image represents a cat or it represents a dog. Then the next thing at the point of modeling is the train test split. Train test split basically implies that you have a data set of cat and dog, and you're trying to split the data in a chunk of the data for training and a chunk of the data for testing. And there are some cases whereby it's not just train and test, it's train, test, and validation, whereby you have a chunk of the data for training, maybe 60% for training, 40% for testing, and then the other 40% for validation of what you've tested, so as to know if your system is generalized based on the metric or the performance of the system. We have different types of metrics. We have accuracy, we have precision, we have F1 score, and some other types of metrics to be able to evaluate the performance of the system. Then modeling, of course, in this case, it's either a CNN model or a transfer learning model. Then once you're done with the modeling, the next thing you have to talk about is evaluation of the model. Evaluation of the model. So you're trying to see if the model has performed well or if it has performed woefully. Next is transfer learning, which is the bone of contention here. So what we just talked about is the steps with respect to convolutional neural network, the training of the convolutional neural network. So what does that also imply when we're talking about transfer learning? So first and foremost, I want to explain what transfer learning is. Transfer learning basically implies that you have a model that has learned on a vast number of data sets or vast number of data, computer vision data, and you're now trying to take a portion of that data. You're trying to take the model and you're now trying to make it learn on another data. So you don't just take a model and make it learn on another data. It basically means, what are we trying to talk about here? We're trying to say you take a model that has learned on a lot of data that is related to the data that you are trying to localize your model to. So for instance, ImageNet was pre-trained on a lot of image data, different types of classes. It has learned how a house looks like, how a car looks like, how human beings look like, the different edges, figures, shapes, and the likes. Now you now want to be able to recognize, let's say, so it has learned on a lot of data actually. So let's say you now want to pre-train it on cats and dog, right? Because it's a model that has learned on different type of data. Do you understand? When you now take it into the cat and dog space, there's a very high chance to be able to learn because there are similarities. It knows how a cat looks like, a dog look like. Most of those information have already been pre-included when it was training, when they were training it on very large amount of data. So training it on cat and dog literally implies that it's going to be an easy pie. All right, so that's what transfer learning is all about. You don't want to take a model that has learned on a very different data scope, right, and you want to bring it into a scope that is entirely different from what it has learned from. No, there has to be some level of similarity in what the pre-trained model has learned with respect to what you want to apply the pre-trained model to learn or to localize. When I say localize, instead of it knowing all the 1000 classes or 800 classes or 500 classes that it has been able to learn across board, you're now trying to let it pay attention to just maybe 5 or 10 classes, or maybe 2, in this case 2, dogs and cats. All right. So transfer learning, basically examples of pre-trained models include ImageNet, ResNet, VGG, Inception, EfficientNet. So you might want to just go brush up on what these pre-trained models are and how they were. There are a lot of papers on them online, so you can Google ImageNet and then you see a lot of information with respect to ImageNet, ResNet, and VGG and the likes. There are a lot of other pre-trained models too that you might also want to check out or give it a try. All right, so what are we supposed to take notes when we are talking about transfer learning? Number one is pre-trained models. You need a pre-trained model. When we say pre-trained, a model that has already been trained on a particular or on a vast number of data. That's pre-trained model. Then you need to fine-tune. Fine-tune basically means you take that model, you now train it on on your own new data set or on your own data set. That's fine tuning. All right. And of course, you need to also tweak the parameters, um, you know, tweak the parameters to be able to learn some new features with respect to your data. So that's fine tuning. Then feature extraction basically means you're trying to extract some important information from that um, from that data. That is, the model is trying to extract important features, understand important features. So for instance, understand that okay, there's the high, there's the air, right, and there's the mouth, there's the nose, and all of those things. These are important features. Then normalization basically means that you are trying to like scale the data to one. These images are pixel values of between 0. Each pixel is between 0 and 255. So you want to be able to normalize to make sure that the data is between 0 and 1. And then transformer, right? That is, you want to be able to run some transformation on the data. Okay, so you want to be able to take a data or create a transformer pipeline. So transformer in this case is different from the transformer that we're going to talk more about. That it's transformer in this case can also be a model, right? But transformer in this case is that I'm trying to pay attention, that I'm trying to communicate to you here, has to do with how you take a data and then transform it into your desired function or your desired system. Also, we also have the transformer, which is um, a GPT, a generative pre-trained model, which I'll be talking about in future class, whereby I'll talk more deep, dive more deep into what it's all about. I hope we were able to get to that point whereby we talk about it. All right. So, why do we need to use transfer learning? Now, transfer learning reduces training time. Then it also reduces computational resources, and then it also does what we call faster experimentation. When we say reduced training time, the reason why it is reduced training time is because one of the reasons why when you train a model it takes a lot of time for it to learn is that a model basically needs to learn every feature. So that convolution thing that I explained in the previous class is trying to learn all the features in that image. It's trying to understand what is this, what is this, what is this, what is. So it takes time. But when you have a model that has already learned all the features and you are just bringing it to learn some very few new features, definitely it's going to take less time to train compared to you are building your own model from scratch to learn all these features or all the new features on the data set. So transfer learning reduces training time. Then of course it reduces computational resources. It reduces computational resources because at the point of training it needs to save a lot of information into its memory. It needs to acquire some new information, learn some new information. But in this case, it has already learned virtually some very key information. It's just trying to learn very few. So it's literally just consuming less amount of memory data or less amount. It's doing less compute in order for it to learn those new features. Compared to you are training it from scratch, whereby it needs to run a lot of computation to be able to learn all the features. And of course it's a faster way of experimenting. So that's the reason why I'm introducing you to transfer learning. So what are the steps involved in implementing a transfer learning? Before we go into the hands-on with respect to this, first you need to choose a pre-trained model. So you could say you want to use a ResNet model or an ImageNet model or a VGG model, right? So you have to choose a pre-trained model that suits your data. Then you need to modify the model. Now, how do we modify the model? You can freeze the pre-trained layers. So the pre-trained model has a lot of layers, all right? So you just want to be able to freeze some certain part of the layers in order for it to be trainable, while the others don't have to be trainable. This is what we mean by less computation, because it doesn't have to learn all the features, all right, in the new data. Then you also need to pre-process the data, that is, prepare the data for processing. Then data augmentation, that's optional. Data augmentation is only needed if you don't have enough data and you want to just scale up your data set from, let's say, 500 to, like, let's say, generate some new data from this same 500, so that you can now have, let's say, 2000 data. Okay, then the next thing after data augmentation, which is optional, is defining your model architecture. All these things I'm going to demonstrate it. So define your model architecture, that is, you need to script out how you want the model to be built. Then compile the model, that is, specify the loss function, optimizers, metrics, then fine tune it, that is, train the model. So this is the step involved in transfer learning. So what then, one of the things we are going to be doing next after training our CNN model and also training a transfer learning model is that we are going to be comparing the performance of a transfer learning model with respect to a scratch implementation of a convolutional neural net model on the same cat and dog model. So let's get right into it and let's dive real deep into it. Okay, so first and foremost, you want to be able to import some of the libraries that you will need. So one of the major libraries that you're going to be needing in this case is PyTorch. So import PyTorch like this. Then in PyTorch we have some packages that we need, like the NN model package in PyTorch, and then we also have some other packages that we need to import. So some of them you just have to follow through with me. Import torch.nn as nn, then import torch.optim, that's optimization, as optim, that's optimizers. Then import torch.nn.functional as f. Then also we have torch vision, because we are dealing with vision data, vision model. So we have a package in PyTorch called torch vision for vision related data manipulation and the like. So you want to have from torch vision import data sets, models, transform and transforms. All right, then from torch.utils we need the utils folder too in PyTorch. Let's import the data loader, and also the data set class. All right, so once we've done that, let me see if I can. So once we've done that, you run the cell. Okay, I want to be able to see if I can. All right, so next is we also need some other interesting libraries, like of course our NumPy, matplotlib as plt. Then we also need import os, that's for working with files. Then we have sys. Then we also have zip files. We need zip files because we are going to be downloading the data set from Kaggle, which is a zipped file, and we're going to be extracting it. So for training our model, I need to specify some parameters that I'm going to talk more about those parameters, but I want to pre-specify them, So some of these parameters we're going to be using is the learning rate. So we want to put learning rate to be, let's say, we can always come back to modify this. Let's assume the learning rate of our model is 0.001. But I'll come back to why I'm setting it. But I just want to preset them. Learning rate, then let's just have batch size to be, let's define it to be, let's say 100, and let's say the model is going to train, let's say 10 times. So let's just have these variables predefined. Then next is, you are working with Google Colab, you want to train a model, you need to ensure that you have CUDA enabled. So how do we know that CUDA is, I'm not sure I've enabled the CUDA, but let's see. How do we know that CUDA is enabled? Yeah. All right, so if you run if you run this device and you call device, it says CPU. All right, so which means we need to enable CUDA. So you come to runtime, you change runtime type here, and then you click on T4, that's GPU. Then of course disconnect and this add. So it basically switches it to its GPU counterpart. So once you do that, it's restarting the kernel, and then you can run all of these things again. So run all these cells again, and let's see what device is going to look like. Device should be GPU, because if you are running something on GPU, it's fast, but if you are running it on CPU, it's extremely slow. All right, so while that is running, we need what we call open data set. So I'll talk now. Of course, device now is CUDA, so we now have our GPU enabled, so it's GPU is enabled. So we want to be able to download our data set. For training. So we need what we call open data sets. So and I'll tell you how we're going to download the data set using open data set. So, but we need to pip install open data set first, and the reason why I have to do that is so that once I run import open data sets as OD, that is going to run. All right, so now let's download the data set from cargo. So wget, so wget is a Linux term for downloading zip file. Is a Linux downloader instruction to be able to download files into your laptop. So this time around we want to download from cargo, a zipped file from cargo. See dogs versus cats versus train.zip, and then you have wget https tests 1. Okay, so let's download. All right, let's be very certain that it's downloaded. Okay, let's see. I'm not sure it's downloaded, but because I'm seeing kilobytes here. Okay, 66.4 MB, 2.04 MB. So let's see. So let's unzip. That would validate if it's downloaded the data, and if not, so let's unzip the data. Okay, that means it didn't download. So first and foremost, we want to ensure that this properly downloads. All right, so okay, yeah, there's one more thing we are supposed to do. So od.download, let's that was the reason why I just knew that there was something missing. od.download https www. cargo.com slash, so it's a competition dataset, dogs versus cats. All right, so let's see, this should work right now. Open dataset od.download. Okay, sorry, let's take note of this. Is cargo.com, not cargo.com. All right, so in this case it will have to ask for your username. So what's your username? Then of course in this case you have to get your Kaggle key and enter this. So getting your Kaggle key, visit your Kaggle profile. So I think cargo.com slash so I have an account. Let me see if I can get into my account. And of course you've got to sign in, and then so in your settings you can visit your settings to get your Kaggle keys. I want to believe that you've been able to get your Kaggle key. So get your Kaggle key, copy and paste that there. So, and if you don't know how to get your Kaggle key, you might want to do some Google search to figure out how to get your Kaggle key. But once you log into your Kaggle account, because you can't access this data set except you are a Kaggler. All right, so download the data set and let's get right to work. So just take, try and look for how you can download that. All right, so let's unzip this data set. So now we've been able to download data set. So unzip slash content slash, so you have to specify the directory of where the data is. So cats, dogs versus cats, train.zip, then unzip. All right, so let's unzip. It's inflating, it's unzipping the data. All right, okay, so this is the data here. Train test 1. Then let me reload this page. I think it's still unzipping. Okay, it's done. So test 1, you can see all the images, 1, 10, all these are real images. Okay, it's a lot of data. And then you also have of course this is the data sets, yeah, dogs, cats, then train. Okay, train is still loading. All right, so this is it, cat.0.jpg, and a lot of other images like that with respect. Then you also have that of dogs right there. All right, so let's collapse this and let's continue what we're doing. So next is we need to specify, we already have the data set, so let's specify some key information, like base dir is /contents. So that's the base dir of where the data set is. So what's the train dir? Because you need to specify what's the path to your train data set. So content/train, then test dir is content test 1. All right, so let's just take a look at some of the data. So because this data is JPEG, they are image data. So let's see if we can look at the contents of our train data. And then so train list is globe.globe, So os.path.join. So we want to be able to check out for anything that is .jpeg. All right. Then we also want to be able to check out for anything that the same thing for the tests. os.path.join test dir. We already specified those path .jpg. So let's see what's the dimension of how many images do we have in our train data. So it says we have 25,000 data. So how many do we have in our test data? It says we have 12,500 in our test data. Okay, let's take a look at some of these images. Let's take a look at. So to take a look at some of these images, we can use matplotlib, but let's use peel. Okay, I already imported this. So let's just pick images at random. mp.random.randint out of 1 to 25,000 data that we have in our train data. Just give me 10 random. So let's say fig is equals to plt.figure, that's a matplotlib. I is equals to 1. So for idx in random index, so random index gave us 10, so random 10. So fig dot add subplot dot. So basically we're trying to create a subplot for this particular index, right? Put it there, then open the image based on the index for that particular image, load that image, and then show the image in that particular index. So next is let's turn off the axis, and then let's show. So let's run this and let's see. From peel import image, sorry. So we can basically see these are some of the data that we are dealing with. This is cat. There's a dog. This looks like a cat, I think. This is a dog, cat, dog. Okay, so it's making sense, right? So now the thing is, we have this data set train, but we need to be able to prepare the data into cats and also into dog. But first and foremost, we need to understand how the data was saved, or how those images were saved into that folder for the train folder. So we have train lists. So let's just get one of the images. Train list 0. Train list 0 is literally one of the first image in the train list is a dog, right? So if we take train list 0 dot split by this, so we want to get this, so we have to split by this, then we need the last index, that's the last entry. The last entry is this, because when you split by this, you have this as the last entry. So you have this 1, 2, and this is the last in the list. So then you split again by dots, and we want the first. So for every so that's a dog. So it basically means, so we can basically loop through every image in train list to know which one is a dog, which one is a cat, which one is a dog, which one is a cat. But if we do the same thing for the tests, let's see, are we going to get the same thing? Oh no. So it basically means that test list 0 doesn't look like so it's just a random image. You don't even know if it is a cat or a dog. Okay, so basically means we cannot use tests underscore. We can't use the test folder or the test list directory, so we need to use the train list. So train list, we're going to use the train list. Let's not forget, if you print the length of train lists comma length of test lists, that should give us an idea. Okay, so test is just to run inference, take a random image, and you want to be able to predict, is it a cat or a dog? You don't even know, because the way the image is even labeled, you don't even know if it's a cat or a dog. So in this case, let's just work with our train list to train our model into, since we have 25,000 data, so let's have the train test split. So from sklearn dot model selection, okay, train list, so test size 0.2, so 20% of the data of this 25,000 would be used for testing, while 80% will be used for training. Okay, so if we look at len train list and then val list, so we have 20,000 and then 5,000 for validation. Okay, so let's do what we call though this data does not require data augmentation, but I just want to demonstrate data augmentation. So in this case, what you need here is what we call the transform, or like the transform. I call it transform actually, but in PyTorch it's called the transform. So we have the train transforms, right? And then you have to write it like this: train transforms compose. So train transform compose takes in all the random transformations you want to. You just want think this transform compose takes in the data set, and then it takes random images, and then it does the transformations you want in order to be able to generate some more data. So what we have here is for instance, you want to have transform resized. Let me even, so instead of using auto, let's do it ourselves. Transforms dot resize. So resize the image to 224 by 224. So for every image that goes through this, resize it to 224 by 224. Then transforms dot random resized crop, so that's 224. Then we also have transforms random horizontal flip. Then of course, then we have transform. You can also have transform to, you have to convert the transform to tensor. So what this does is that for the trained data that you're trying to augment or you're trying to process, we can also use it for augmentation. You can also use it for data pipelining. So because most of the data in the train data, all of them are not of the same dimension. All the images are of different dimensions. So we want our model to be aware of just one dimension of how the image is going to look like. So what we are telling it is that transform.compose, the first thing is you take that image, you resize it to 224 by 224. So whatever the image is, input image, or the data you're dealing with that you're trying to apply this transform to, then you also do a random resized cropping to 224. I'll give you that as an assignment to also go and learn more about that. Then transform or random horizontal flip. Horizontal flip basically means you're flipping the image. You're just randomly flipping the image horizontally. Then once you're done, you take the transform and then you convert it to a tensor. That is, we want the data as a tensor because we're feeding it into a GPU. Then finally you can also normalize the tensor. But in this case, I'm not sure we need to do the normalization. All right. So we have the train transform. So I also want to have the val transform. Let me see. Transform. Val transform. The same thing we are doing for train, we are going to do apply to the val. Then we also want to have the same thing for the test, because we are also going to run after training. When we are done training, we evaluate on our validation to know what our training looks like, the performance of our training on the data that we are aware of. Then test is for data that we are not even aware of. We don't even know what it looks like. So you want to also have the same level of transform across all of them. All right, so let's create our data set. So to create our data set, we're going to be using the data set class, and we're going to be using the data set attribute class. So let's create a data set, let's create a class, call it data set, and let it inherit touch.utils.data.dataset. You remember I already imported that from the start. So first and foremost, let's have what we call set.file def init self. Then we need file lists, that is train lists, test lists, val lists. Then we do a dot transform. Then we can also pass in the transform, because this needs to be running on data. So we are passing in. So if it's a train list, so it's train list and then train transform in order to generate our train data. Then if it's a test list, it's a test list, then test transform, val list, val transform. All right, so the _len, right, is a method just such that once you call the data set, right, it gives you the length of what your data looks like. All right, but the most important thing here is the okay, let's also have return self.file length. All right, so next is load one of the images. So let's load one of the images. So take an image. So let's use the get item attribute. Let's write this ourselves, but let's call it idx. All right. So the get item attribute, you're taking an image path, which is self.file lists, then the index list, then index. Don't forget, index is a number between, let's just say, 0 and the file list, that is the file length. So let's say the train data is 20,000. So index can be, let's say, 10,500 or 10,049. Okay, so you just want to take that particular image, get the path to that particular image, then you want to load the image. So you want to open the image with PO, then you pass in the path, and then the image transformed, the transformed form of the image, self.transform img. So self.transform is this. So of course you're passing the transformer, which is any of this, depending on the type of data set you, maybe it's a train data or a validation data. And then of course, how do we get the label? Like we illustrated earlier, label is gotten from the image part. So the image part, if you remember this, which is in the train data, we have this train data, you have this, right? So dog, right? Which means this will apply for train and tests, train and val, but not, it won't apply for the tests. So we have label. So we get, once it is a dog, we are saying okay, call it a 1, and if it's a cat, call it a 0, and then it returns the transformed image, which is the input to the model, which is a 224 by 224 by 3, and then the label, which is a 0 or a 1. So we have an image an image of dimension 224 by 224 by 3, and we have the label, which is 0 or 1. All right, so this is making sense. So we've defined this. So next is to create our train data. So train data is basically data set train list, then passing the transform. Val data is data set val list, then passing the transform. Test is data set test list, then passing the, but you know that this test data won't most likely work because the labels won't be dog or cat. So we can just take this off. We're only working with the train data and the val data. So next is, let's load in the data. So we need what we call a data loader. We already imported data loader because we're about to train the model, but we want to be able to pipeline this data loader. So we want to be able to pipeline the model into the pipeline the data set into the model. So we have what we call train loader. Train loader is more or less like you're trying to zip both the input and the output, which is x and the y. The x is the 224 by 224, which is the image, and the y is a corresponding class, either a 0 or a 1. So you have a train data loader, and of course you want to ensure that you set shuffle to be equal to true. So that is that. So now we have our train data loader. Let's check what's the dimension of a typical data. Train data 0. Train data 0, that's the image, right? The image and the label. So let's get the image 0, and then let's check the dimension. So you know that, okay, that's the, then train data for this particular image 0, 1. It will tell you it's either, and this is a 1. So this particular image is a dog. Yeah, dog is 1. All right. So now our data is ready to be trained. So next is, let's implement CNN from scratch, and then train the model. So I already taught you how to implement a CNN, so I'm just going to just look at as I implement something similar to what you are familiar with. CNN self dot init. So let's define self dot layer. Okay, sorry, self, I didn't define this. Def init, apologies. Self. I was just wondering why is it in my mind I already wrote that. Self dot layer 1. So nn dot sequential. So sequential, that's a sequential block. So in this sequential, we want to have nn dot conv 3d. Okay. So we want to have convolution 2d convolution 3, then 16. Right, input 3, output 16. Filters, kernel size 3, padding 0, stride 2. Then this is being fed into the batch num to the 16. Then relu as the activation function, and then max pooling layer 2D. So that's layer 1. So let's have like 3 layers, I think. Self dot layer 2, nn dot sequential, nn dot conv 2d. So in this case, let's have input 16, output 32, batch num 32, relu, max pool. Let's have another layer. Self dot layer 3, nn dot sequential. Alright, so this one is 316, this one is 16 to 32, then this one is 32 to 64. I think that suffices. So now the next thing is the fully connected layer. So fc1, nn dot linear. Let's have 3 times 3 times 64. And then let's have 2, cat or dog. All right, so 2 classes. Then self dot dropout. So we are applying dropouts. So we want dropout to be 0.5. So we're just defining all these things. Let's have self dot fc2 to be nn dot okay, I think that should be all, since we already have the target to be 2 actually. So it will compress all these so the output of this layer 3 fed through this then gives us a binary of either it's a dog or a cat. So let's have dropout and then self dot relu. Self dot relu is nn dot relu. Alright, forward self x. So out is equals to self dot layer 1 x, then out so layer 1 x, self dot layer 2, self dot layer 3, then out dot view, out dot size 0. So you're trying to retransform and then view it we transform the dimension so that the dimension matches with the next layer. Then of course fc1 and then relu as the output. Alright, so then we return output. Okay, return output. Okay, alright, so let's run this. Okay, we have a little error. This wasn't tabbed. So index. Pay attention to index. Okay. So indentation error. So you have to ensure that on indent, we still have an indentation error at line 4. Okay. Okay. Non-module name type shared. Where is that coming from? No, I didn't. Alright, so we are good. So now let's load our model. So model is equals to CNN, then to device. So we are moving it to, don't forget device is CUDA here. And then we're also setting it to the training mode. Touch.nn has no attribute ReLU. 27. Line 27. So it is capital RELU. Okay. Touch.nn has no attributes. Okay, sorry. The E is a small letter. Alright, good. So our CNN has been defined. So next on the list now is for us to specify the optimizer. Optimizer, let's use Adam, and then our criterion, that's categorical cross, that's cross entropy loss. For then don't forget our learning rate, we already specified our learning rate to be 0.001, and so we're about to train. So next is to train the model. So let's train the model. Epoch is 10. We just want to train for 10 epochs. Of course, I will want you to train for longer epochs, but I'm just going to train this for 10 epochs and then see the performance of the system on 10 epochs in train loader. So data is equals to data dot to device label to device. Don't forget we moved the model to device here. So model is moved to device, so it's on CUDA already. So the data now, we're trying to move the data to device so that they can all run on CUDA, right? And then you feed in the data, which is that is already on device, fed into the model, and the model attributes a class. Then you evaluate the loss with the criteria, and then of course optimizer 0, grad the optimizer, and then do backward propagation, and then in step. All right, so but we need to evaluate the accuracy of the system, which is after each epoch. So accuracy is attribute argmax. It's going to be giving you two different classes. So class 1 could be 0.9, the other one could be 0.1. So you want to know which one is 0, which one is 1. So that's why we're using attribute.argmax label, then if it is equals to the input label, which is 0 or 1, right, dot float. That is how we are able to evaluate the accuracy for that epoch. We are running it for every epoch. So for that particular epoch, we want to be able to have epoch loss, epoch accuracy, right? So for epoch 0, what's the loss, what's the accuracy? For epoch 1, what's the loss, what's the accuracy? So basically means we are taking 25,000 data and we are training it, 20,000 data for the train loader. We are training it, that's 10 times. All right. So so to aggregate the epoch accuracy. Epoch accuracy is simply the addition of the accuracy of that current image divided by the length of the train loader. That's the epoch accuracy. And then the loss definitely is the addition with the loss. So epoch loss is simply plus the loss divided by the length of the train loader. So that gives us what we want. Next is to print it after every epoch. Let's print, because we want to be able to see epoch. We want to be able to see what we are training. Train accuracy. Train loss. So then we can format it. So epoch plus 1, because epoch is starting from 0 actually. So epoch plus 1, so we can have it from starting from 1. Then epoch accuracy. Then epoch loss. Then another thing we want to do is that is, you train, you evaluate. You train, you see the accuracy of your training. So, but for every epoch, we also want to be able to evaluate what we want to be able to evaluate. So, with touch.nograd, so this case we want to run it through the val loader. So epoch val accuracy. So you train, you have your epoch accuracy, training accuracy, epoch training loss. Then we can also have epoch validation accuracy and validation loss. All right. So just like we have the train, we have val output is equals to model data. So val loss is equals to criterion. Okay, so we do the same thing. So val loss, criterion val output label, then the accuracy is val output. That will give us the 0 or 1. Then we can be able to evaluate if it is evaluate the accuracy. Then epoch val accuracy plus length val loader. Then epoch val loss plus equals to val loss divided by the length of val loader. Then we can also do the same thing for print. Epoch val accuracy, val loss, and the likes. All right, I think we're ready to train the CNN, right? So next is to run the model. Okay, incomplete input. So what is missing? Print this format. Epoch loss, epoch accuracy. So why is it incomplete? Okay, line 39. Okay, yes. Okay. All right, so let's run this. So the model is running. It's currently here. This green arrow lets you know where the model is. So you run this. This is going to take a little while. So I'm just going to pause and I'm going to come back right after this model is done training. All right. Welcome back. So the model started learning. This was trained for just 10 epochs. There's room for improvement. So training accuracy started with 60%, and then at 10 after 10 epoch it ended at 73%. Then validation accuracy was started at 65 and ended at 73. So you basically see that the train and validation accuracy, there's no much disparity. It's generalization, so it's not like it's overfitting. But this data needs more training. So it basically means out of 10, it will predict, out of 10 samples, it will always predict 7 accurately, and it might misclassify 3. All right, but of course there's room for improvement. I would advise that you train this for maybe a longer epoch, maybe like 10, maybe like 20 or 30. All right, so that you can see better performance. All right, so let's go ahead to do some evaluation, on the test loader. I'm not sure we implemented a test loader, but let's duplicate it so that we can just load the test data. Test loader. Let me just take it down, break it down here. So we have the test loader. Okay, test data is not defined. Let's define that. So this is a data that we've not seen, the model hasn't seen. So we want to test the little time we've spent, that the model has spent training. We want to see the performance of this model on this data. Okay, so while we're waiting for this, okay, so now let's run some inference on maybe some random 100 data samples. So so one way to predict, you want to be able to, okay, let's say dog probabilities. What's probability that all these 100 samples are dogs? Okay, so dog probs is equals to a list, and then we want to like set the model to an evaluation state. So with touch.nograd, that is no gradients computed at this point. So whatever we're doing right now, there's no gradient computation. So for data, file ID in test loader, let's not forget test loader, this is the input image, but this is the file ID, not the class. Right, in our val data and train data, it's data and then the label. When this time around, it's the file ID. So let's say data is equals to data dot to device, and then prediction is equals to model data. So prediction is model data then, but since it's going to be attributing, that's the logic, attribute logic. So we want to know if it is a dog or a cat. So prediction list is equals to f dot softmax. Softmax the prediction, the dimension equals 1. Then we're trying to take all rows, single first, and then column 1, then to list. Yeah, that's the prediction. So dogs probability is an extension list, then the zip of the zip of the file ID and the prediction, the corresponding prediction. All right, so let's run this. So if we say, since we know what docsprop is the file ID and the prediction, that is the percentage prediction with respect to dog, that's why we have 1 here. That's why we have 1. The first 0 is cat, but we're trying to see the prediction, the probability that a particular image is a dog. All right, so dogsprops, let's view what it looks like. Dot sort key lambda x int x0. So what is dogs props? So we have to sort it. So let's sort and let's wait. So it's running on the test loader. Don't forget, test loader is from test list. So test loader is simply, let me take this out, length of test list. That's 12,000. So we just ran inference on 12,500 data points. So if you run this, you basically see that the probability of an image being a dog is the probability that this input image is a dog is as shown below. So this image 1, there's a very high chance that it's a dog. There's a very high chance a dog is a dog. 5, not so sure. So it's a 50% chance. But of course, if you train this data a little more, we should be able to have a much more. But let's run some display. Actually, let's do some display. We should be able to have some much more better accuracy. So let's not forget the class name. Let's remember what our encoding based on. So label, dog is 1, cat is 0. Dog is 1, cat is 0. So class names, so we have 1 dog and then 0 is cat. So let's write a function that can do the visualization for us. Visualize model prediction. So what's the model and then the image path. So let's assume model is in a training stage. So model.train, model.eval. So we want to know if it was training at that point, if it's still in its training stage, so we can set it to evaluation. So image is equals to image.open, image path, test transform, img, image transformed, then of course image transform dot unsqueezed, then image transform dot device, and then touch dot no grad image transformed. So let's look at the predictions. Let's evaluate the predicts. Max output along the axis 1. So let's plot. Args is equals to plot dot subplot 2 to 1. Axis is off, and then let's print the predicted item. Print item, and then let's set the title f predicted class name predicted item and then player2.imshow. Then of course set the once you are done evaluating, then set the model back to its state before this. All right, so we have this. Let's randomly pick any test image. So that will be np.random.choice. Test lists. Test image path. Test image path. So this is a test image. So let's visualize model prediction, test image path. Let's take this out. So plt.ioff, plt.show. So let's see. Good. So it's predicted that this is a dog, which it's actually a dog. Let's run another. Let's see. But let's not forget we still need to do some more training. This is a misclassification. This is not a dog. This is a cat. Okay, this is a dog. Why is it calling it a dog? Yes, this is a dog. So 3 classes were correct, 1 misclassification. Good. This is a cat. That's correct. 5. That's 4 out of 5. 4 right, 1 wrong. 5 right, 1 wrong. So it has only missed 1 wrongly. A cat. This is correct. This is 6 right, 1 wrong. 7 correct, 7 right, 1 wrong. Cat. 8. This is correct. 8 right, 1 wrong. 9 right, 1 wrong. So our model actually performed well. I said out of 10 it will predict, it should be able to at least get 7 correctly, but this time around it got 9 out of 10 correctly in prediction. All right, so next is transfer learning. Let's do what we call transfer learning. So for transfer learning, we have different types of models. We have different model implementation, but in this case we want to just stick to maybe ResNet and see how our model is going to perform well with respect to ResNet. So like I said, you import all the libraries that you need. Import PyTorch. I think this time I will need touch summary. From touch summary, import summary. That's because you want to be able to look into the summary of the model that you implemented. Import touch.nn as nn, then import touch.optim as optim. Don't forget we already have data set, so we are not doing the data pipeline. It's just to model it out and feed the model inside. Import matplotlib.pyplot as plt. Import touch vision.transforms. I'm writing all these things so that you can have them at the back of your mind as transforms. Import touch vision.transforms. Okay, from touch vision.transforms import to tensor, normalize, So from touch vision the data sets import from touch vision imports data sets, then from touch.utils data import data loader. So we are running this on cats and dog. I want your assignment to be on CIFAR 10. So CIFAR 10 is a publicly available data set. You can even import the data set from Touch Vision. You can even get CIFAR 10 from Touch Vision dot datasets import CIFAR 10. Then we also have MNIST. Alright, so I want you to work with this data set, just play around with them. Then one last thing now. This is transfer learning, so we need pre-trained models. So how do you access pre-trained models? So we do from touch vision dot models import touch vision model as models. Import touch vision dot models as models. So let's run this and let's see if we are on point. So one of the models we want to work with is let's try out ResNet 50. So model is equals to models.resnet 50. So pre-trained true, and we want to load this to device. So we want to move this model to device. So that downloads. The model is not heavy, just about 100 megabytes. Okay. So now we want to do what we call modification of this ResNet. Like I said, ResNet was trained on a lot of data, so we want to be able to let it work for just cats and dog. So let's create a class of modified ResNet. So modified ResNet. So we can have self.resnet is equals to touch.up. So this time around we need to load the model pytouch/vision ResNet 50. This is another way you can load it pre-trained. Alright, so we have .resnet. Yeah. So for param itself, in self.resnet, setting all the grad, that is, we are not trying to compute gradients across, so we're not computing the gradients, so thereby reducing computational strength of the model. So self.resnet.fc is equals to nn.linear, then 2 class. Alright, then forward resnet, then it would predict 2 classes. So we want the linear to whatever the previous layers is, the last layer, which is a fully connected layer, we are resetting it to 2048 and then predicting 2 classes. Alright, so and that's that. So now the next thing we want to do right now is we already have our data loader. We have our criterion. Let's not forget criterion is equals to nn dot cross entropy. and then we have optimizer, which is equals to nn, which is optim dot adam model dot. Okay, but in this case, what is model? Model here is modified ResNet. Model here is modified ResNet. Then to device. So so now next is model.train. Set it to train mode, and then next is for us to proceed to training the model. So literally we are just taking the same code that we wrote the last time, the same code that we wrote here. We're taking the same code that we wrote here. So let's go through it again. So we have the train loader, which is data label, then the model has been defined as ResNet with 2 labels. So we feed it into the model, and then so let's run this and let's see. Let's run this. I hope we've not missed anything out. So once this is done training, I would sync up back for that so that we can evaluate it together. So this is a much more robust model, so we expect it to do better. All right. So looking at this, you will see basically that this same 10 epochs that we applied for CNN, and we applied the same 10 epochs to ResNet, and you could see that the performance of the model is far better than that of the CNN, and that's because ResNet is more robust. It's a pre-trained model. All right, and you basically see started straight off at 92% training. Validation was 93%, and it ended at 95.48, 95.94. So it basically means that the model is robust. It generalizes well. So it basically means that if out of the 10 that we did earlier in the CNN, it got 9 correctly, this is most likely going to get everything correctly. So the model is great, and you see that the model, as at epoch 2, it was already at 94, 93. Let's say epoch 3, 95, 94. So it just maintained that pace, until epoch 10. So it wasn't dropping, neither was it decreasing. So let's take a look at let's run the inference and let's see. We already have what we have. We have this test image, yes. So we'll just take it, pass on the model, and run it. So when we do that, let's see what we have. So let's see what we have. Okay, great. This is correct cat. So if we run it again, that's 1. Cat 2, that's 2 correct. The third one also is correct. Cat 3. Let's try again. This is correct. Dog 4. This is correct. Dog 5. This is correct. Cat 6. This is correct. Dog 7. This is correct. Cat 8. This is correct. Dog 9. This is correct. Cat 10. So you could see that this one, it predicted every of the tests that we tried running this on accurately well. So that's to let you know that Pre-trained models are far much more better than CNN models. That is, if you are able to use them appropriately. All right. So basically, take a look at the assignment. Please make sure you work on the assignment. Run it on CIFAR 10 data set. I hope you've been able to learn something great.
Congratulations. I want to say that I'm so proud of you for your intentionality in listening to me as I tutor you with respect to deep learning for computer vision. All right. So you've learned what pre-trained models are, and I've been able to illustrate different kind of pre-trained models that you can leverage on in building your own personalized and tailored computer vision model for whatever problem you're trying to solve. All right, I want you to know that I have a little assessment for you. Yes, I know that. I know that. I have a little assessment for you. It's quite very simple, and it's going to be shared via Google Classroom. So walk through that notebook step by step, right? And analyze that particular data, build the model, and I look forward to seeing your results. Look forward to seeing what you come up with. I look forward to seeing you in the next class. Stay tuned.